Hey guys, welcome to a new video in this computer vision tutorial. In this video here, we're going to talk about corner detection. So first of all, we're going to talk about like what is really a corner in an image, and then we're going to talk about some different kind of corner detections, methods that we can actually like use to detect corner in images. And then at the end of the video, we're going to actually like implement methods or like these methods here to do corner detection on images that we load in. But first of all, remember to join the Discord server. I'll link to it down in the description here, and you can come join our community where we talk about different kind of stuff within computer vision, deep learning, artificial intelligence, and stuff like that. And if you have some projects where you have some problems, you can ask your questions in there, or if you just want to find some inspiration. You can also become a channel member here on the channel here if you hit the blue button under the video here, and you can support the channel even more than you're currently doing with a small monthly fee, and everything from it will go to make better quality and also make more content in the future. So just I really appreciate the support. So let's now jump into the first slide here where we're going to talk about corners in images and different kind of features in images. So where we have features in images, we actually like have, for example, like corner and edges and stuff like that. And in the previous video, I showed you like what edges are in images and how we can find edges in images and what describes an edge in an image. But this video here, we're going to cover more and talk about more about corners. But when we have, like, for example, we find corners in images, then we can actually like find matching points between frames of an environment. So if we have multiple frames, we can actually like find matching points from those frames, and then we can relate those images to each other and extract information from that. So if we, for example, want to recognize or like detect one object from one image to the other and relate those two to each other, then we can actually like use corner detection methods and algorithms to detect the corners and then match those points together and find this relationship between the two frames. So features are uniquely recognizable in images, so that's why we can use, like, for example, corner detection to relate images together and stuff like that, because the features that we're detecting, like for example like edges and corners and stuff like that, are uniquely recognizable. And as just mentioned here, we have different types of features in images. So for example, we have edges that we talked about in the last video, and then we have corners, which is actually like just interest points. So we have, like, for example, one point of interest, which is a corner, like for example here on the roof. We can see here at the roof here, we can see, like, for example, a corner here, and that will be an interest point. And we can also have different kind of features, which is blobs, which is just like kind of like a region of interest. So if we're talking about corners, it's actually like just one point that we're interested in. But when we're talking about blobs, we're actually like looking at a region that is in our interest. So a corner is an intersection of two edges. So when two edges meet, then we actually like have a corner. And a point so a corner is like a point in which the directions of the two edges change. So when we're actually like talking about edges, we have these different kind of gradients that we can calculate for the point to see if they're actually like on an edge. And when we're actually like detecting corners with the gradients here, or like if we want to determine if those two edges that meet is actually like a corner, then we can see that when the gradient has like a high variance, because then we know that that the edge is actually like changing, or like that we have an actual like corner because the pixel intensities in the neighborhood around that point is actually like changing very high, because we have a high variation in the gradients. So how can we find corners in images? So first of all, we're going to determine like a corners values for each pixel, so we can produce a corners map. So we're actually like just going to look at all the pixel values here in our image, and then we're going to determine like a corners value. So if we want to say like if this is a corner or if it's not, so we set up like a corners values for each pixel. So we're looking at like the changes in intensity and stuff like that, and then we determine this corners map where we have like different kind of like could this be a corner in the image by looking at this value here, or is it not a corner in the image? And then we can use non-maximal suppression, as we already talked about in the edge detection video, where we have like multiple responses, and then we compare that response or that pixel value to its local neighbors. So for example, if we have like a corner here on top of the roof here, then it could maybe like detect a corner, like a three corners here around the rooftop here at the edge here, or like at this corner here of the roof. But then we will use non-maximal suppression, and then when we have multiple responses, then we compare each corner that we have detected to its local neighbors, and then we find the best one of those. So instead of having three corners up here represented, we will only have the best one and one in that case here. So we just find one corner here for this rooftop corner here. And then we can actually like threshold the corner in this map to get the most significant corners. So this is the approach that we're taking and the procedure that we're going to use, and some of these different kind of corner detection algorithms and methods implement. Where first of all we're going to determine these different kind of corners values. Then we're going to use non-maximal suppression to filter out some of the noise, and then we're going to threshold the corners map again to only get the most significant corners, because we don't want like each time there's a change in the intensity and two edges meet, then we don't want to specify that as a corner, but we only want to get the most significant corners in our images. So the first corner detector here that we're going to talk about is the Harris corner detector, and we're going to look at some of the math behind it from the papers that they published to actually like implement this corner detector. So when we're looking at the Harris corner detector, it actually like looks at the variation of intensity. So when we're looking at the intensity of like the pixel values, then we're actually like going to look at the variations of that to actually determine corners and edges in our images. So we have this formula here where we can actually like determine the variation of intensity. So we're going to sum off all the pixel values here that we're going to throw in our image. So we have the XY here, which is actually like the pixel values, and then we have this V here, V function here that depends on X and Y, because it is just like a window at position XY. So we have like a window that we can like slide over our image to actually like see the variation of intensity. So when we're looking at a window, we're just looking like at a region and finding the variation of intensity for that region or window. And then we actually also have this I here of X and Y, which is the intensity at that specific position, so at that pixel value that we're looking at, then we're looking at that specific intensity, and then we're going to subtract that from this value here, which is the intensity at the move window. So when we're actually like moving our window by a factor here of u and v. So when we're actually like sliding a window here by some factor, then we will get another intensity. So we're actually like just comparing the intensity from that pixel value that we're looking at to the pixel values in the move window that we're moving around with this u and v here. So we can actually like look at the changes in the intensity, or like the variation of the intensity in our images. And then we actually like get the variation of our intensity when we actually like sum all of those values up here when we run through our whole image. And then it will be stored here in this E here that depends on UV. And then we can actually like use Taylor expansion to rearrange. Like we don't really want to know like or like specify what is going on here. We just need to know like the like intuitive way here what is going on, and we're using Taylor expansion and stuff like that. Then we're rearranging some of the terms, and we put it on matrix form. So in this example here, we just have this M matrix here, where we're going to sum all of these things here. So this is just on matrix form, this formula up here, where down here we can actually like use Taylor expansion to use Taylor expansion of this one up here to get in this matrix here. So this is just like the intensity here in the X and the Y direction that we actually like take the derivative of. And in the last video we talked about the Subpixels operator, which is really what we use when we're taking like the derivative or in images, because we're taking this approximation of the derivative of the intensities here in both the X and the Y direction. And then we'll get this matrix up here that we can then rearrange and put into another matrix form here. So we actually like get this result here that we can then use later on. So this is just like the math behind, and we shouldn't like really know what is going on like behind the scenes here. We should just know like this is like the overall things that are going on. We're using like some Taylor expansion. We're looking at the variation of intensities. We're doing some differentiating or like we're using the Subpixels operator in our image in both the X and the Y direction, and then we'll do some rearranging of the terms and stuff like that. And then when we have done that, we can actually like calculate a score of the probability that it is a corner. So when we're looking at a pixel value, then we can calculate a score for that pixel value, which corresponds to the probability that this is a corner or not. And this is where we take this R value here, which is the score of the probability. And to actually calculate that score, we just take the determinant here of the M matrix that we have up here. And then we also have like some K value here that we can specify, which is like kind of like a threshold for our probability. And then we use this trace here to the same matrix here again, and then we square the result here to actually like get the probability that this is the corner. So this is just yet another formula that we're just going to use because it has been published, and this is like the official way to actually like calculate the probability from this Harry's corner detection algorithm or method here, where we can see here that the determinant here is actually like the eigenvalues here for like the first one here and the second one, and the trace m here is when we add these two eigenvalues here together, and then we can have a window here with a score r that is greater than some value is considered a corner. So we're looking at a threshold that we set, and then if that r value is over that threshold, then we say that this value here, or like this pixel here, is a corner, and if it's below that threshold, it will not be a corner. So if we look at an example here of the Harry's corner detector, and we're going to see how we can actually like do this here in code at the end of the video. Or we can see the result here of the Harry's corner detector in an image here with the house. So we can see that we get some corners around here on the rooftops. So these are really good corners here that it detects. But we also over here in the trees and over here to the right, we get some false positives, and it thinks that all of these different kind of like leaves here on the trees is actually like corners, because we have some edges that meet, and the change in intensity is also there, and the values here is above some threshold. So think that all of these different kind of like corners here in the tree here is actually like corners, but we can use some different kind of methods and threshold values to actually like reduce some of the false positives here that we get in some of these corner detectors. So I've just talked about like the different kind of like eigenvalues and eigenvectors, and this is just to like shortly give you an introduction and intuitive introduction to what is really like eigenvalues and eigenvectors, and how we can use them to find corners in our images. So we use them from a linear algebra, where an eigenvector is changes like an eigenvector changes by a scalar factor when a linear transformation is applied to it. So over here to the right, we have like, for example, like an eigenvector here with our input, and then it changes by a scaling factor here, which is this eigenvalue here, when we're applying a linear transformation, which is this a matrix here, which is the linear transformation that we apply here to a vector. And then the eigenvalue is the actual like factor which the eigenvector is scaled. So this is the gamma value over here, which is the eigenvalue, and this is the factor that we scale this eigenvector here with. So we have this u here, which is our eigenvector, and we have the eigenvalue here, which is the gamma value, and then we have a linear transformation here that we apply to our eigenvector, and that will be the same as when we have like an eigenvalue here that we like is a scaling factor to our eigenvector. And when we're actually like applying linear transformations and stuff like that, like what's really going on if, like, for example, we have these two vectors here, and then we apply a linear transformation here, for example, for this eigenvector here, then we'll actually like have a change here, or like a linear transformation here of one of the vectors here, and that can actually like be the same as saying like we change this eigenvector here with some eigenvalue, which corresponds to doing this linear transformation of the eigenvector. So we can use this actually here. We actually use eigenvalues and eigenvectors to determine corners in images, and some of these different kind of corner detection algorithm actually like implements these approaches, or like these methods here for eigenvalues and eigenvectors to find corners in images. So the next and the last corner detector here that we're going to talk about in this video here is this Shitomasi corner detector. So it uses eigenvalues, as we just talked about, to detect corners, and it kind of takes the same approach as the Harry's corner detector. So it calculates the corner quality at every pixel in the image, and then we specify if that is a corner or not by some threshold. It uses non-maximal suppression, as we already talked about, and the corners with minimal eigenvalues less than some threshold are rejected. So it uses the eigenvalues to detect the corners, and then it filters out if it's a corner or not by some threshold value. And then the remaining corners are sorted by quality is in descending order, and then we can actually like specify how many corners do we want to see in our image, and we only want to see the corners with the highest quality, because we're sorting the corners with the highest quality in descending order. And then we can throw away the corners where there's a better corner at a distance less than a maximum distance that we can specify. So this Shitomasi's corner detector here is actually like really good, and it takes the same approach as the Harry corner detector, and it uses eigenvalues. We can set up some threshold. We can specify like how many corners do we want to detect in our image, and then we can also specify like the distance that we want between all of our corners in the images. So this is an example of the Subpixels corner detector here, which is kind of like the same as the Harris corner detector. We can see that up here in the roof we get really nice corners detected here in our image. We still get some false positives over here in the trees, but not as much as we did with the Harris corner detector, and we can even like tune the parameters even more that we're going to do in code. And we can also specify like the max distance between the corners here need to be larger or like greater, so we don't get as many corners detected over here in the trees, and also up here in the roof. Like we can specify max distance that is greater than the distance between those points here, and then we'll remove all the different kind of false positives here close to each other. So when we're going to compare the Harris corner detector versus the Subpixels here, we can actually like see the code here for implementing these algorithms or methods here in OpenCV. So the first one here is the corner Harris here, where we just specify the input image, and then we specify the output image where we're actually like going to show the corners that we're detecting. And then we need to specify the neighborhood size here, the aperture parameter here for the subpixel operator. So these are just the different kind of parameters that we need to specify for the functions or like the procedures that we specify that I showed you and talked about here in the slide. So we know when we're doing the Harris corner detector, we're looking like at a window that we're sliding around, and then looking at the neighborhood, and then we specify the neighborhood size here in this function, and also the a parameter for the subpixel operator, and then we have a Harris detector free parameter here that we can tune around to see like the results of our actual corner detector. Where when we're talking about the Subpixels corner detector here, we have some different kind of values that we can change on. So we have a value here that we can specify the maximum corners that we want to detect in our image. So in this example down here, we can actually just specify that we want to detect the best 10 or like the 10 corners in the image with the highest quality, and we only want to detect those in our image, and it will remove all the false positives down here in the trees, for example, and some of the corners here that lay really close to each other. We can also specify the minimum quality of the corners, so the minimum quality before we don't really see them as corners anymore. And we can specify like the maximum distance here, or like the minimum distance here between the returned corners. And we also have some different kind of like size of an average block for computing a derivative covariation matrix over each pixel neighborhood. And we also have some free parameters for the Harris detector here that we can like tune around to get the best results when we're using this. So when we're comparing the Harris corner detector to the like the Subpixels corner detector, we have some more different kind of parameters that we can tune on in the Subpixels, but the Harris corner detector is also really good, and we're going to see that in code. So this is just to show you the result of, like, for example, when we're comparing the Harris corner detector to the Subpixels when our image is not really that complex as before with the house. Then we can actually use both the Harris corner detector and Subpixels corner detector to detect the exact same corners in our image. So we just have this chessboard here, which is really simple, and we can see that it takes all the corners here with both methods, and we don't really need to tune any parameters for those two. We just play around with the default ones, and we can, in simple and really like really simple images where we have these different kind of, like, for example, really high changes, like for example here on the chessboard, then we can both detect all the corners here with both the Harris and the Subpixels corner detector, and it won't really make a difference like which one of those we use. So I also want to show you like how we can do corner detection in Subpixels. So this is just a way to find more exact corner position by using Subpixels. So when we have one pixel, then we actually can divide that into Subpixels, and normally that is integer pixels. So we divide it into Subpixels, and then we just do corner detection on those Subpixels again to find the exact corner position of those Subpixels. So we actually get a way more accurate position of like where that corner actually like is in the image. So if we want to find the exact position of that corner, instead of just like saying that this is like a corner here at that pixel, by not going into like the Subpixels and finding the exact corner position. So if you have some applications where you want to use that, we can also do corner detection in Subpixels. So the last one here is that we can actually create your own corner detectors. So we can create our own corner detector like the Harris and the Subpixels corner detector. So when we create our own corner detector here, we need to find the eigenvalues that we talked about, and also the eigenvectors to determine if a pixel is a corner, because when we're using eigenvalues and eigenvectors, we're actually like looking at like the transformations and the differences between the pixel intensities, and then we find the minimum eigenvalues for the corner detection, and then we use those to actually like determine if this is a corner or not. So it's actually like possible that we can create our own corner detectors as well, just like the Harris and the C2MASI corner detector. So we're now into Visual Studio here, and I'm going to show you the different kind of code examples that I just showed you in the slides here in code. So first of all, here we're going to create a function here for both the Harris corner detector and the C2MASI corner detector. So in this example here, we're just going to have some matrices here that we're going to store the different kind of outputs in. So like both like the output here from the corner detector and stuff like that. So first of all, here we're going to have two images here that we're going to read in and see two examples of. So the first one here is the chessboard that I showed you in the slides as well, and then we're going to see the house as well here. First of all, we're checking here if the image here is empty, and if it's empty, we see out in this error here that there was an error loading the image, and we couldn't like load in the image here from the directory that we specified up here. Then first of all, here we need to grayscale our image here, so we call this function convert color here. So first of all, we pass in the input image and the output image where we want to store that grayscale image. And then we just specify here that we want to convert it from BGR to grayscale image in this example here. And then the grayscale image will now be stored in this gray variable here. First of all, here we're going to im show the original image up here, so we can see like the original image, and then we can also see the detected corners in our images. Then we're going to have this output here where we're just going to like initialize it with some zeros here in the matrix or in the image that we can then specify later on when we're actually like doing our normalization and converting to like absolute values, so we can actually like show our detected corners. Then we're calling this corner Harris function here that I showed you in the slides, where it takes in the input image and the output image, and then it takes the neighborhood size, so the neighborhood, the size of the window that we're going to look around of the neighbors when we're actually like determining if this is a corner or not. And then we're going to specify a parameter here for the Subpixels operator, and also a free parameter here for the Harris detector. So these parameters are just the same as we just talked about in the slides. Then we're going to normalize the things here, so we're going to convert the corner values to integers so they can be drawn on the actual image. So we need to specify or like convert the values here to actually like integers, so we can display and draw them on our image where we actually like detect the corners. So we're going to just use this normalize function here, where it just takes some parameters here that we're just going to use in this example here that I'm going through the code. And then we convert the output, the normalized output here. We convert that to like a scaled absolute value. And then when we have that, we can actually like draw the circles around the corners that we have detected in the image. So we're just going to have two follows here that just runs through the different kind of corners that we've detected. So we have the corners in this output norm here, and the output norm here, where we're just looking at the rows and the columns here of the circles that we're detecting. And then we're just going to draw a circle of those points that we have to actually like detect the corners in. So we to actually like draw a circle here, we just call this circle function here. We take the image where we want to draw that circle, and then where we want to draw that point, and this is at I, j, because this is at the pixel value where we have actually detected that circle. And then we just specify like how large the circle we want, and also the color of the circle and stuff like that. So this is just two for loops to actually like run through all the pixel values where we detected a corner, and then we draw a circle around that corner that we have detected in the image. Then we can actually like display the result here. So first of all, we're just going to resize our image, and then we can just show our image here with the actual circles that we're drawing up here on our image. And then we just specify this wait key here so we don't terminate our program, and it will keep up the frames here that we're actually like showing. So if we just go down here and run this first Harris corner detector here, I'll just comment this C2MASI corner detector out here, and we run the program. And we see where we're loading in the image, we're doing the operations on the image to actually like detect the corners, and then we can see here that we're showing the results in this example here. So we see the original image we have over here to the left, and then over here to the right we have the actual like the corners here that were detected on this chessboard here with the Harris corner detector, as I showed you in the slides. So if we just take the other image here as well, so we're going to do that for for the digital mass edge detector here as well. But I'm not going to show you with the chessboard here because it will just give the same result. But in this case here, we're going to use the house image instead, and I'm just going to comment it in here as well for the Harris corner detectors, so we can display them side by side here at the end. But if we go down here to the corner detector, we're just doing the exact same thing and using the function that I showed you in the slides. So first of all here, we're going to read in our image. We're going to read in an image from this directory here where we have stored the house image. We're going to check if our image is empty. After that, we convert it to a grayscale image. And then down here, we can actually like have a vector here of points, of 2D points where we have where our 2D points is float values. And this is just a vector where we'll store all the corners that we can then later on draw on our image. Then we use this function good features to track, which is actually like the built-in function to implement this Shitsumashi edge detector. And then we just specify all of these different kind of parameters here that I'll show you in the slides as well. And we can play around with some of these parameters here. If we, for example, get like too many corners in our image, then we can change that to 20, for example, and we will only get the 20 best corners that were detected in our image, and it will be stored in these corners here. And then we're only displaying or detecting the 20 best corners in our image. And we also have these other different kind of parameters here with, for example, the minimum distance between the return corners. So if we don't want to have like that many false positives or like corners detected close to each other, then we can specify like a higher minimum distance here between our returned corners. And then we also have the other different kind of parameters here that we went over in the slides. Then when we have all the corners detected in our image stored in this vector up here, then we can actually just go through our corner vector here and then just display each of those corners here on our image. So we do the exact same thing as with the Harris corner detector, where we use this circle function here to actually like draw the corners that were detected here. And then we just specify the color and the size of the circle that we're going to draw around that corner that we have detected in the image. And then at the end here, we're just going to resize our image again, and we're going to show the actual output from our Shitsumashi edge detect our corner detection. So we go down here and run both of these edge detectors here at the same time, so we can compare them and see like what they detect. So if I run the program here, it will now call both these functions here and do edge detection for both of them. So the first one here, because we have a wait key here, I need to tap one key before the other one comes up. So we can see here to the left that we have this output of the Shitsumashi edge detector here, where we see we don't really have that many false positives anymore, because we have specified that we only want 20 corners in this image here, and we only want the best ones with a minimum distance to each other. So that's why we don't get that many corners detected over here on this image compared to the output of the Harris corner detector out here. And we won't really get the same exact same results as I showed you in the slides, because in the slides I had 100 as the maximum corners that we want to detect, and this example here we only have 20. So it takes the 20 corners with like the highest quality, and it will only display those on the image here in this example here. So we have some different kind of parameters that we can tune on with the Shitsumashi edge detector that we can do with Harris. So there's both some pros and cons with both of them. And when we have like a complex image here where we want to detect the corners, then we should probably use the Shitsumashi and play around with some of the parameters, specify the distance between the corners that we want to detect, which is specific for a specific image, and also the maximum number of corners, because those parameters play a really huge role when we're doing edge detection or like corner detection on our images. Where over here to the right we have this output of the Harris corner detector, where we get a lot of false positives. We could maybe remove some of them by tuning some of the parameters as well. But if we have like more simple image, like for example on the chessboard, it doesn't really matter if we're using the Shitsumashi or the Harris corner detector for detecting corners in very simple images. So in this video here we're seeing like the different kind of methods and methods on like how we can use corner detectors to detect corners in images, how some of these parameters here that we can tune them, and what these parameters actually like does, because those depend on the different kind of like algorithm and method that is implemented in these things here with the eigenvalues and eigenvectors that we went over in the slides. So thank you guys for watching this video here, and remember to hit the subscribe button and bell notification under the video here, and also like this video here if you like the content and you want more in the future, because it just really helps me and the YouTube channel out in a massive way. I'm currently also doing a deep learning tutorial where we're talking about like neural networks from scratch and like what's going on in neural networks, how neural networks learn and stuff like that. And we're also creating neural networks from scratch, training it on a data set and doing predictions on data that it hadn't seen before. So if you're interested in neural networks and deep learning, I'll link to the tutorial up here and you can go check that out. Or else I'll just see you in the next video, guys. Bye for now.